In this video we start the analysis of a BJT amplifier, and first of all there's many types of amplifier circuits, but we're only going to analyze the most common, which is a common emitter BJT. That's what the CE stands for, is common emitter. So this is what the circuit looks like. Here's our BJT NPN. Here's one of our sources, VCC. Here's our source on the base side, which is 1.5 volts. And you can see now that this is a practical circuit because we do have resistors connected to the BJT. Here's a transistor connected to the collector, RC. 15K is RB connected to the base, and 1K RE is connected to, connected to the emitter. Alright, this is the emitter. Now notice that in a different color in red I have a capacitor and an AC signal. I'll talk about the purpose of this capacitor in a later video, and then also VI, this AC signal, that's the signal we actually want to amplify. So from a big picture conceptual point of view, often with amplifiers there's some sort of AC signal that you want to amplify. Okay, so we want to make this AC signal bigger at where the output is, which is V0. That's this node here with respect to ground. That's where our output voltage is going to be. And the cost of amplification of this AC signal is the DC energy that we supply to the circuit with this 1.5 volt source and also this 15 volt source. Okay, so we're not going to get a bigger AC signal here at the output for nothing. Okay, the cost is the DC energy that we supply to the circuit that gives the ability of this transistor to amplify. And as we talked about in an earlier video, the BJT has the ability to amplify the current on its collector side compared to its base side. And when we put it in a circuit like this with some resistors and voltage sources, we'll see that we actually get an amplification, a bigger signal in amplitude of the AC at the output compared to this input AC. Alright, well, to start with, and this analysis will take a couple of videos, and we're just going to do a portion of the analysis in this video, and that's to find what are called the Q values, where Q here stands for quiescent. Okay, so we're going to find the quiescent values, and what the quiescent values are, they're the base current, collector current, and V0 for DC only. So when we find these Q values, we ignore this AC source. In fact, we're going to ignore the capacitor in the AC source in this analysis. That's why I put it as a different color. That's why I put them in red. Okay, now one item that I left out of this example that I just remembered is that on the data sheet for the BJT, okay, so BJT data sheet, we get that the beta spec for this transistor is 100. Alright, we're going to need that in the analysis. Alright, so first we're going to calculate what the base current is. Okay, so base current is traveling in this path here. Okay, that's our IB. And to find what the base current is, we're just going to do a Kvl equation. So come down here, KVL. Starting at this 1.5 volt source, we're going to have 1.5, then minus 15K IB. Also on this data sheet, we're told that this transistor is silicon. Okay, and we need to know that because that will give us what voltage drop we use here from VBE. So if it's silicon, our VBE is going to be 0.6. Okay, so this is VBE. Alright, and continuing on, now when we get to the 1K resistor, Okay, now the 1K resistor not only has IB flowing through it, but also, as we saw in the earlier conceptual video of how a BJT amplifies, the emitter current has both base current and collector current. Right, so emitter current's equal to IB plus IC. Alright, so you see that's our Kvl equation for the base loop. Now, as you see, when we're finished here, we've got two unknowns, IB and IC. So, in order to solve for IB, we plug in here that IC, when you're using a transistor as an amplifier, and under the assumption that we're in the active region, where beta is equal to beta spec, well, IC is just equal to beta spec times IB. So we're going to plug in for IC 100 IB, right? Because 100 is beta spec. So IC is just equal to beta spec IB. And in this course, anytime you're told that we have an amplifier circuit like this, you can make the assumption that we're in the active region and that we can use this relationship between IC and IB, that it's related. Those two quantities are related through the beta spec of the transistor. So now if you go ahead and plug into this, you'll get that IB is going to be 1.5 minus 0.6 over 116K. Okay, right? Because when we put in 100 IB here, we'll have 101 IB times 1K, which is 101K IB. And then we also have a 15K IB here. So that's where the 116K comes from. And then 1.5 minus 0.6 is the difference in voltages here of the source voltage and VBE. Okay, which again is just the drop across the forward bias base to emitter junction of the BJT. It doesn't look like it's going to let me write this E here. Okay, E. So 0.9 divided by 116K will give an answer of a base current of 7.8, and that's microamps. Okay, so that's one of our values. Okay, because remember, there's three of them here, three Q values: IB, IC, and V0. Now IC, as we just saw a moment ago when we solved the Kvl equation, IC is just beta spec IB. See, this equation here is always true as long as you're in the active region of the IB curve that we talked about in the previous video. Okay, which again, you can always assume this in this class. And if we're analyzing a BJT amplifier, this will always be true because we'll always be in the active region. So IC is just 100 times IB, so it's going to be 780 microamps. Alright, so that's two of the three. Now we're just left with V0. Okay, well V0, that's the voltage at this node here, okay, which is attached to the collector of the transistor with respect to ground. So it's the voltage between these two nodes. Well, the easiest way to get V0 is just to take the voltage drop that's across this resistor RC and subtract it from your source voltage VCC. So V0 is VCC minus the voltage drop across RC. Okay, and this is just going to be 15 minus IC times RC. Okay, where IC is right here and RC is 10K. So you plug in the numbers and it comes out that V0 is 7.2 volts. Alright, so that's our third Q value. Alright, now we'll continue on in the next video looking at, well, how do we account for this AC signal, which after all is a signal that we want to amplify. Okay, how does that figure into this analysis? That's what's next.